Morning everyone. Welcome to the first segment on analysis of parallel magnetic circuit. In this segment, we will be seeing some general guidelines that help you to solve numericals on parallel magnetic circuit. So, first of all, what is a parallel magnetic circuit? A magnetic circuit having two or more than two paths for the magnetic flux is called a parallel magnetic circuit. That is, a parallel magnetic circuit will have more than one flux path. Take a look at the following magnetic circuit. Here we can see that the flux produced in the limb PU has more than one path to travel. That is through QT as well as through QRST. So the flux phi at the point Q will split into two, phi 1 and phi 2. Here we can see that the path QT is parallel to the path QRST. Similarly, in the second phase, the flux produced in the central limb has two paths to travel. One path is via the left limb and the second path is via the right limb. So these two are some typical examples of parallel magnetic circuit. We know that a magnetic circuit is similar to an electric circuit. In case of an parallel electric circuit, the total current equals to sum of currents and EMF across the parallel path are same. Similarly, in a parallel magnetic circuit, the total flux will be equal to the sum of flux and MMF of parallel path will be the same. So these are some of the general guidelines that will help you in solving the numericals on parallel magnetic circuit. So this is the first case. In this figure, a coil with n number of turns is wound on the side limb. So when a current I is passed through this coil, a flux phi will be set up in the coil. So in this figure we can see that this flux phi will split into two, that is phi 1 and phi 2. So this is an example for parallel magnetic circuit. Let phi be the flux in the path B, A, C, D. Let L be the length of this path and A be the area of cross section. So the reluctance of path B, A, C, D is S is equal to L by mu 0 mu R into A. Similarly, let phi 1 be the flux in path BD, L1 be the length and A1 be the area of cross section of path BD. Then the reluctance of the path BD, that is S1 equal to L1 by mu 0 mu R into A1. And let phi 2 be the flux in path BEFD, L2 its length and A2 the area of cross section of BEFD. Then reluctance S2 of the path BEFD, that is given as S2 equal to L2 by mu 0 mu r into A2. So we know that a magnetic circuit is similar to an electric circuit. Then the electrical equivalent of the above magnetic circuit can be drawn like this. So the total MMF, that is Ni, and it is the source which produces the flux phi. So this flux phi is traveling in the path BACD, and its reluctance we are denoting it as S. So reluctance is similar to resistance. Then this flux phi is splitting into two paths. One is phi 1, which will travel through the path having reluctance S1, and the second is phi 2, which travel through the path having the reluctance S2. So from this figure, it is clear that the total flux phi, that is equal to phi 1 plus phi 2. So that is the first equation. Then what we can say? Phi 1 S1, that is parallel to phi 2 S2. So if two paths are parallel, their MMF will be same. So what we can say that phi 1 S1 will be equal to phi 2 S2. Then what about the total MMF Ni? So total MMF Ni, that will be written as, if you are considering the inner loop, what we can write, total MMF Ni will be equal to phi s plus phi 1 s1. Or considering the outer loop alone, Ni can be written as Ni equal to phi s plus phi 2 s2. So these are the four basic equations that are required to solve the numerical on a parallel magnetic circuit. So always remember that the flux in the length where the coil is wound, that must be taken as phi. Now the second case, consider this figure. So this is the figure. Here we can see that coil is wound on the central end, but there is also an air gap in this case. That is the difference. So the flux phi is produced in the central end. This flux is having two parts. One is phi 1 and another one is phi 2. So here also this is an example for parallel magnetic circuit, and we can see that the flux path B, A, F, E, that is parallel to the path B, C, D, E. So let phi be the flux in path B, G, E, and L be the length of the path BG. Listen here, L is only the length of the core, the length of the flux path BG, and A is the area of cross section of the core. So reluctance S of the path BG, S is the reluctance of only BG, and that is given as S is equal to L by mu 0 mu r into A. And similarly, if you are taking the L gap, through this L gap also the same flux phi is passing. And I'll let Lg be the length of air gap. Then the reluctance of this air gap, that is Sg, is equal to Lg by mu 0 into A, since in this case mu r equal to 1, since the material is air. So that's regarding the reluctance of the central limb. Similarly, in the case of left limb, let phi be the flux through BAFE, and let L1 be the length of BAFE. So area of cross section A1 will be A1 is area of cross section, area of cross section of BAFE, that can be taken as A1. Hence, the reluctance S1 of this path, that is given as S1 is equal to L1 by mu 0 mu r into A1. Similarly, if phi 2 is the flux in path BCDE and L2 its length and A2 is the area of cross section, the reluctance of the path S2 is given as S2 equal to L2 by mu 0 mu r into A2. Now, The electrical equivalent of the above circuit can be drawn like this. Here we can see that the source is placed in the central limb. The source is Ni. Then in the central limb, the flux is phi, but this flux is traveling through two materials. One is having a reluctance S and the another one is having a reluctance A gap. Sorry, another one is having a reluctance SD. And this two material they are connected in series. So the equivalent of the central lamp will come like this. Now similarly, the phi 1 flux that is traveling through a reluctance of S1 and the phi 2 that is traveling through a reluctance of S2. Okay. So from this circuit, what we can conclude? Total flux phi that is equal to phi 1 plus phi 2. That's the first step. Then what regarding the parallel paths? We know that BAF is parallel to BCDE. So the MMF will be the same. That is, we can write phi 1 S1 is equal to phi 2 S2. Then regarding the total MMF, consider the right loop. We can write total MMF Ni that is equal to phi into S plus Sg plus phi 1 phi 2 into S2. Similarly, what we can write Ni is also equal to phi into S plus Sg plus phi 1 S1. So only difference is that we have to incorporate the reluctance of the air gap. All the other things remains the same. So whenever you get a question, first thing we have to write is the phi. That is in which length the coil is wound, the flux in that limb must be taken as phi. If you're taking that point into consideration, everything we can do easily. So that is the end of the first segment on analysis of parallel magnetic circuit. In the second segment, we can see some numericals on the parallel magnetic circuits. Thank you.